Welcome to a video on section 3.7, derivatives of inverse functions. You might recall from the first week that an inverse function is a function that undoes the original function. In other words, it goes in reverse. It's more than reverse though, it's a reverse and undoing. In essence, it swaps the domain and range, right? So inputs become outputs, outputs become inputs. Now for this to work, it has to be one-to-one and onto, but one-to-one meaning for every input. Of course, to be a function, for every one input, there's exactly one output, but one-to-one for every one output, for every element of the range, there's exactly one point in the domain that gives it to that, so we can map them back and forth. It is true that if you do f of f inverse of x, you're back to x. It is also secondarily true, although not necessary for this section, that f inverse of f of x will also equal x. In other words, those functions undo each other. A very easy way to think about that would be something along the lines of like, well, if f of x is equal to x plus 3, that's a function that adds 3, then in your head you could probably think, well, a function that would undo that would be x minus 3. And if you put one of those inside the other, like if you did f of f inverse of x, you would be putting f inverse into f. You can think of x minus 3 plus 3 would just be back to x. So it would cancel each other out. Okay, now let's get into the calculus piece of it, which is, here's our first thing, the derivative of an inverse function. Let f be a function that is both invertible and differentiable. That's important. It has to have a derivative, and it has to have an inverse. Then the derivative of the inverse. So it looks like f negative 1 prime. The way we would say that out loud perhaps is the derivative of the inverse function of f is equal to 1 over f prime of f inverse of x. It looks a little bit like a composition. Well, it is a composition of functions. It's the inverse plugged into the derivative. Now, I have provided a proof here, and I don't prove all of these, but this one's kind of fun and clever and worthy of it. So what you do is you start with the identity. It is true always that if it's invertible, that f of f inverse of x is just x. So what I want to do is take the derivative of both sides. So I took this left side, just wrote a derivative in front of it. The right side, I just wrote a derivative in front of it, here and here. Took the derivative of both sides. Now let's do the easier side first. Let's just take the derivative of the right side. We know from the power rule from section 3.3, the derivative of x is just going to be 1. So that's easy enough. That's not too bad. The left-hand side, though, you might think of, oh, wow, that looks a lot like the chain rule. Well, it is the chain rule. The chain rule says take the derivative of the outside function. The outside function is f, so f prime. Leave the inside alone. So this is basically the same as that, but I just took the derivative of f, times the derivative of the inside piece. The inside piece is the inverse. Okay, so then if I just divide both sides by this factor, you can see that I'm dividing both sides by that, then I get to this final stage here, which is actually my derivative inverse formula from above. All right, let's take a look at some examples. So to do that, we're going to be identifying what is the function, what is its derivative, what is the inverse function. All right, taking a look at number 1. If f of x equals x cubed, find the derivative of the inverse function of x using the formula above. Okay, and then there's more, but there's more. Then do the problem once again by first finding the inverse function and taking the derivative of it. So what we're trying to do with number 1 is use this new equation that we have here, but then also that it'll seem true because we know a little bit about how to find inverses. So let's use that definition. So the first thing we want to do is we want to figure out what is f prime of x, and that's pretty easy. We'll just use the power rule. The derivative of x cubed is 3x squared. Okay, and we're also going to want to find the inverse function. So let's do a little bit of that work here. If f of x is equal to x cubed, then the inverse function, remember you can just write that as y, the inverse function is found by just swapping x and y. So the inverse would be x equals y cubed, and then just solving for y, we'll take the cubed root of each side. The cube root will cancel out the cube, and we'll be left with the cube root of x is equal to just y. And so that's my inverse function. And then I'll just rewrite this as inverse. Since I did the inverse here, my y now is the inverse y. So that's f inverse of x is equal to the third root of x. Okay, so now we want to put all of the pieces together by looking at our formula. What we're really trying to do is this 1 over, I keep pointing to this, look at all the arrows we have, 1 over f prime of f inverse of x. But I really want to analyze what is this denominator first. Okay, what that means is put f inverse into f prime. I'm going to put the two elements next to each other here. We already found that f prime of x is 3x squared. That's on the left. But now we've learned that f inverse of x is the cube root of x. So those are the two pieces we have already. Now this mouthful up here, this f prime of f inverse of x, all that means really is put the inverse function into the prime function. Put this function into the derivative. And so all we're going to do is write the derivative. It's 3x squared. But instead of writing x, right, instead of 3x squared, we're putting in the inverse. So we're going to put the third root of x in there. All right, now let's write down our derivative of our inverse. I had to get my mouth situated here. So now we're ready to do it. So f inverse, the derivative thereof, using the formula, is 1 over all of this that I just figured out. So it's 1 over 3 times the cube root of x squared. And so you can write it like that. But it also, another alternative form of writing it is to write the square on the inside. So it's 3 times the cube root of x squared, something like that. All right, we'll end up with the same value either way. Now, we want to do this a second time, so it did ask us to do it. It says, then do the problem once again by finding the inverse function and then taking the derivative of it. Well, we already found the inverse function here. What if we just took the derivative from there? So let's try it that way. If f inverse of x is the cube root of x, and we can write that as, remember, we can write that as 1/3 power, then the derivative of that function, we could just use the power rule. You might be thinking, why didn't we do this earlier? Oh, you'll see as we go on. So let's use the power rule. Bring the power down, 1/3. Reduce the power by 1. 1/3 take away 1 is negative 2/3. If you rewrite this, you have 1 over, we got this 3 down here already. Remember, x to the negative 2/3 means reciprocate it, 2, so it's x squared over 3 is the third root. We have an identical answer. This probably felt way easier, and in that case, it was easier. So what you're going to want to do with this formula that I have above is always ask yourself, is it easier just to find the inverse and then just take the derivative of it, or will it be easier to use this formula? So it just, and of course the answer in math as always is, it depends. All right, I'm going to try to exclusively focus on this formula because that's really what I'm trying to teach here in this section. All right, number 2, if g of x is 2x cubed minus 3, find the derivative of g inverse of 1. So we're going to be plugging in 1 as well. So let's go through the steps. So g prime of x equals, taking the derivative of this using the power rule, 6x squared for the first term. Derivative of minus 3 is 0, so that's my derivative. And then I want to find the inverse function itself. And so there's multiple ways to do this, but let's just go ahead and go through the inverse so you can see it one more time. So if the function is y equals 2x cubed minus 3, then the inverse is doing a swap. Right, this is my inverse. X equals 2y cubed minus 3. Add 3 to both sides. You see that there? And then divide by 2 on both sides. And you get there. And then the last step would be to take the cube root of both sides. And so you end up getting that the inverse, it's not f, it's g, isn't it? So g inverse of x is equal to this expression here on the left, the cube root of x plus 3 over 2. Now, that's a little, you can see that's a little bit messy. Imagine taking the derivative of that. Taking the derivative of that would require the chain rule. And then you have to just think about how the expression x plus 3 over 2 would work in terms of acting like a linear. But so there would be a little bit of thinking there to do the derivative of that. So we're just going to use the formula from above. Okay, remember our formula. Our formula for our for the derivative of the inverse would just be 1 over putting the inverse right here, right? Putting this piece, I'll highlight it, putting that into the derivative, right? So the formula itself says it, like this. It would say, in this case it's not f, it would be g, it would be g prime of g inverse of x. And all that means is put inverse into the function. So all we do is we write it out. 1 over, and it says 6x squared. 6x squared. Don't put x. We're going to replace it with the cube root of x plus 3 over 2. Now, in this particular problem, we want to know g of 1. Excuse me, the derivative of g inverse at 1. So we're going to go ahead and plug 1 into this. So the derivative of g inverse, not of x, of 1 is just taking that expression and plugging in 1. 1 over 6 times the cube root of 1 plus 3 over 2 quantity squared. So we got a lot going on there. So it looks like I have 4 over 2, the cube root of 2. I'll just simplify that a little bit. Right? 1 plus 3 is 4 divided by 2 is 2 squared. And we can write that maybe a little more simply as 6 times the cube root of 4. All right, so that's a little bit of a mess. But it came out nicely at the end. And for this example, I'm not going to do it in the alternative method, but you might think about doing it yourself if you want to pause the video, just taking the derivative directly of that expression and making sure it matches what we got there. Let's move on to number 3. If h of x equals x plus square root x, find the derivative of h inverse of 2. So again, we'll go through the steps here. Maybe one additional step at the beginning would just be to rewrite h of x as x plus x to the half power, so I can use my power rule. Now I'm ready for the derivative of this. It will be 1 plus 1/2 times x to the minus 1/2 power, and that's probably best simplified as 1 plus 1 over 2 times the square root of x. Remember, the negative power is reciprocal, the half power is square root. So that is my derivative function right there, and we're going to go ahead and go to the trouble of finding the inverse right now. Okay, this time I'm going to take a little bit of a different approach, and here's the reason why. If you would try to find the inverse of h of x, you would find it extremely difficult. So I'm going to show you briefly like what would happen, and then I'm going to stop and kind of undo it. So don't write down the notes right now. Wait until I tell you to start taking the notes. But what I've been doing in the past few problems, I've been trying to find the inverse of h of x by writing something like y equals x plus square root x, and then I would say, well, the inverse of that would just be to swap the x and y. So it would actually look something like this. Now, this is where you may begin to be troubled. Like, how are you going to solve for y here? This is something new and unusual, and it's going to be quite troubling. And there's a good reason why you're not going to be able to do this exactly, and it's not going to behave exactly as a function. There's more than one place to do it. So you can see that if you try to solve for y, you certainly don't want to do something like subtracting square root y from both sides, because now what are you going to do? Now you have y on both sides. So that's not a reasonable way to get at this one. And you also can't do anything like just factoring out a y, because then it would be like 1 plus like y times what is square root y is very, very tricky. Like, what would that even be? And so that's not going to be a valid way to do it as well. It'll still involve some y's. And so what happens in this particular problem is you get very frustrated with this inverse and you don't even know what to do. So I'm just going to delete all of that and show you an alternative way to think about it. Again, so now you can start taking the notes now. So what I want to do is I really want to think about this. I want to figure out what is h inverse prime of 2. And I know from my definition that I'm going to need to figure out what. Well, let me write the definition down so you can see what I'm talking about. If I want h inverse, the derivative of that at 2, using the definition, it's 1 over h prime of h inverse of, in this case, 2. I've been doing it with x, but here I'm doing it with 2. So here's the new strategy I'm going to take. I don't want to find the inverse because you just saw me flounder a little bit with it. Instead, I want to think about where this function would track to. I want to figure out what is h inverse of 2 without actually finding the inverse. You might think, like, how is that possible? How could you find h inverse of 2 without actually knowing what h inverse is? Well, the way to think about it is something along the lines of this. So what value can I plug into h so that I get 2? If I can figure that out, then I can have what I need, which is I know that h inverse of 2 will just be the reverse of this. That's what an inverse means. In other words, it will give me back that number that I need. Okay, so that's the dilemma I need to figure out. So we really want to figure out when is the function equal to 2, instead of actually solving for the whole inverse. So I'm going to take the function x plus square root x, and I'm going to set it equal to 2 and solve. Now, this looks a little troubling to solve, but it's not too bad with a little bit of algebra. And you might be able to figure out the one and only valid solution in your head, like what plus the square root of itself is equal to 2. You might notice in your head that 1 plus the square root of 1 equals 2. But you might think maybe there's another solution, and that's very reasonable to think. So let me go through the steps of algebra to show you what's going on here. If you subtract x from both sides, you get square root x is 2 minus x. Then the way you unsquare root is that a math phrase, is to square both sides of this. All right, I'm going to square both sides. On the left, square root of x squared is just x. On the right, you have to distribute 2 minus x times 2 minus x. If you distribute that out, it would be 4 minus 4x plus x squared. Now, if I subtract x from both sides to get a 0, I'm going to put the terms in order. I have x squared. I already have a negative 4x minus another x is minus 5x plus 4, and then this will factor to x minus 4, x minus 1, seemingly giving me answers of 4 and 1. Now, the reason that those aren't both valid is anytime you do a square root equation, you may remember you have to check for extraneous solutions. Are they valid? Well, if you plug in 1, in fact, it is valid because 1 plus the square root of 1 is 2. But if you plug in 4, you get 4 plus the square root of 4. That's actually 6. It's not 2. That's an extraneous solution. So the only valid solution is 1. So what you figure out by playing with this, by setting the equation equal to 2, is you actually found the answer you wanted. You found out the value of 1. When you plug in 1, you get 2. That means, cool news here, that I said this wrong, h inverse of 2 just takes me back to 1. In other words, you just swap the x and the y. So we can get around finding the inverse by just playing with the value we want. Let's finish it off. H inverse prime of 2, or the derivative of the inverse, equals 1 over h prime of h inverse of 2, we found out to be 1. And now all I have to do is plug 1 into the derivative. Now the derivative is the work I did right at the beginning over here. So we're going to plug in 1 for x right there. Now you can do that in your head. Let me just write the work off here. It would be 1 plus 1 over 2 times the square root of 1, because I'm plugging in 1. And the square root of 1 is 1. So you have 1 plus 1/2, and that would be 3/2. And so better written, 1 divided by 3/2 is 2/3. Wow, that's something you'll need to meditate on. You see I did a lot there. Why don't you try pausing the video and doing something similar for number 4, and then turn it back on. We'll see what happens. Okay, let's see how you did. All right, so we've got several things going on here. I want to use this definition of the inverse derivative, but you probably figured out that if I of x is x squared plus 3x plus 2, that finding the inverse is no easy task. So you want to do some not trickery, but something along the lines of what I did. If you want to find the inverse derivative at 2, you're going to have to know the value of I inverse of 2 to do that per the definition. So the way to do that is figure out, when is I of x, when is this function equal to 2? And the reason that that's valid is if we can find the x, then we can know the inverse value. So I'm going to set, and maybe you already did it, x squared plus 3x plus 2 equal to 2, and solve. If you subtract 2 from both sides, you get a 0. If you factor out an x, you should get x times x plus 3 is 0, and the two valid solutions for this equation would be 0 and negative 3. Now, notice I have some extra directions in here. If I of x is this, 4x is greater than or equal to negative 3/2. Well, negative 3 is not in that domain, so we're going to cancel that out as a possible solution, thereby realizing we want the value of x is 0. So what did we learn? We learned, we learned that I of 0 equals 2. Bet you could have done that right at the start. Look, if you plug in 0 into that function, 0 plus 2 is 2. Great, but what does that mean? It means necessarily that I inverse of 2 is, that's correct, back to 0. In other words, you just swap the x and the y. Cool. Now we are almost completely set up. What we need now is we need the derivative. This time I'm doing it a little bit different order. The derivative of I, going back to the beginning, is 2x plus 3, and now we can write down the derivative of the inverse function. All right, let's use our definition, which is 1 over I prime of I inverse of, oh, I wrote x, didn't I? In this case, we want to know it at x is 2. So we're going to put in 2 right here. All right, so we did all this work up ahead so we could learn this, right? Because we need to plug that in here. I inverse of 2 would be 0. So this is 1 over I prime of 0. And if you plug 0 into the prime, or into the derivative right here, right, I prime of 0 would just be 2 times 0 plus 3 is 3. So my final answer, 1/3. A lot of manipulation there. A lot of things to think about. All right, so we'll be doing more of that in class. Okay, now let's take a look at some inverse trig functions. So first, I got to do a little setup for you here. Let's look at the inverse sine function. I want you to recall that the sine of theta in right triangle trig is the opposite of the hypotenuse. When we did our circular trig, we thought of it as y over r. So let me remind you what I mean by that. Okay, like if we go around, now this is any circle, not just the unit circle. If we go around some angle theta, I'm just going to draw it here. Right? If this is theta, if we rotate back this way and we come into this point right here, that particular point will have a y value, right? It'll be some height, and the radius will be the length from here to here. On the unit circle, the radius was 1. But the sine function is opposite over hypotenuse. We call that y over r in general for any r. You can see the triangle I have at the right would be specific to r is equal to 1. And notice I've labeled this x. We're going to come back to why that I've labeled that x in just a second. So if f of, here's the setup. If f of x is sine x, if f is the sine function, what is the derivative of the inverse? So we've got a couple things going on. We're going to just use the definition from above. So we know that the definition says that all we have to do is 1 over the derivative of f itself. That'll be easy to get in just a second. But inside it is the inverse function. So we'll need to know what that is. And so let's figure that out. Let's write it down. Well, f prime, we know from before, the derivative of sine is cosine. So we got that. What is f inverse of x? F inverse of x is going in reverse. So if f equals sine x, then f inverse we just write as sine inverse of x. Fine. Great. It didn't seem too bad so far. So we're just going to do what the definition says. Plug the inverse into the derivative. Boom. I'm going to plug it in right there. Plug the inverse into the derivative. So here's what we get. We get 1 over f prime of f inverse of x. F prime is cosine x, but instead of putting x, I'm plugging the inverse in for x. So it's cosine of sine inverse of x. Okay, so that would actually be valid as an answer, but you can see it looks just a little bit messy, and it would be great if we could clean that up. So hence, this is why I have the drawing off to the right. We're going to analyze this drawing a little bit. So I drew this triangle. This is just a right triangle. I've labeled theta here, right? You can see theta. And I've labeled the opposite side. This is opposite, and this is the hypotenuse. I've labeled the opposite side x and the hypotenuse 1. That might seem pretty random, like where did that come from? Where it came from is where I'm sitting in the problem right now, right? I have that the sine value, I want the sine inverse of x. And so I'm going to be going in reverse. And so I set it up so you can see, check it out, look, I'll write it down over. Sine of theta is opposite over hypotenuse, x over 1 is x. Oh, that must mean that sine inverse, remember, you just swap the x and the y, sine inverse of x is theta. See it? Okay, so I set this up on purpose, so let's go further with this. What is sine inverse of x? Sine inverse of x is just theta. Gives you back that angle there. Great. Okay, now it says 1 over cosine theta. What is cosine of theta? Well, remember that cosine, I don't have it written down here, but write it down. The cosine of any angle, we can write as the adjacent over the hypotenuse. Well, if you look at this picture, I don't have the adjacent side. But I got a little Pythagorean theorem in my back pocket, which is whatever this adjacent side is, right? I'll just put it as a question mark. I know that question mark squared plus x squared equals the hypotenuse squared. Remember, a squared plus b squared equals c squared? Got it. Let's solve for the question mark. 1 squared is 1. Subtract x squared from both sides. Now take the square root of both sides, and you get that the missing side is the square root of 1 minus x squared. Oh, got this solved. That means the adjacent side, as messy as it looks, is the square root of 1 minus x squared. So what is this now evaluate as? Well, it's just 1 over the cosine of theta. The cosine of theta is the adjacent over the hypotenuse. The hypotenuse is just 1, so it's square root 1 minus x squared divided by 1. It's just square root 1 minus x squared. Okay, a lot of work, but now we got something we can memorize. What do you mean we can memorize? We have the derivative of the inverse sine function. That's it right there. Okay, now this is one you might try by pausing the video. This one's asking you to find the derivative of the inverse of the tangent function. Now down below there's a little cheat sheet. I'm just going to move ahead. Here are all the formulas for the derivatives of the inverse trig functions. You can see that I just did this one right here. Right? I just kind of made a proof of this. Of course, these 6 things are things that you can memorize and should memorize. Unless you want to, of course, recreate the proof that I just did. You can see it was quite a bit of trouble. But I'm going to challenge you right now with the, maybe you turn the video off, to try to prove that tangent inverse of x is that one to the right. So when you get a chance, then come back to the video. Okay, so here's a quick check. I'm not sure if you tried it or not, but the derivative of the tangent function would be secant squared x. All right, now we're going to try to attack what is the derivative of the inverse. So we are wanting the derivative of the inverse of the original function. So let's use our definition. It's going to be 1 over f prime of f inverse of x. All right, so we've got a lot going on. So first off, what is f inverse x? Well, if f of x is 10x, then f inverse is nothing more than tan inverse of x. So that's easy enough. That'll be 1 over f prime of tan inverse of x. And then f prime we already found to be secant squared x. So this becomes 1 over, plugging tan inverse into x here, secant squared of tan inverse of x. Wow, what a mouthful. Now what I want to do is I want to set up my triangle over here to the right so that the tangent is x. All right, so here's my theta. If I set up, you may recall up here, tangent is opposite over adjacent. Here's my opposite side. Here's my adjacent side. I want it to be x, so this should be x, and this should be 1, because x divided by 1 is x. Great. I have the value of, let's just go to the next line, the tangent inverse. What is the tangent inverse of x? Well, we set it up so the tangent is x. It's theta. And now I'll have to figure out is what is secant squared of theta. Remember that this is secant theta, whatever that is, squared. Those are the same thing. Well, secant, I need to remember what that is. Secant is the reciprocal of the cosine function. So it's 1 over cosine of theta. Now I can't do cosine of theta because cosine, remember, is adjacent over hypotenuse. I have a missing hypotenuse. So you had to go through those steps of using the Pythagorean theorem again. A squared plus b squared equals, I'll put h for hypotenuse, c squared. And so if you take the square root of both sides, you get 1 plus x squared is h. Great. That is my hypotenuse. This is 1 plus x squared, square root thereof. Great. Now I can do my cosine. My cosine is adjacent over hypotenuse. So it becomes, the secant of theta becomes 1 over the adjacent over the hypotenuse. And so it's quite a bit of a mess, but if you remember dividing fractions, same change flip, this will just come out to 1 divided by is the same as 1 times the reciprocal of this piece, and it'll just be square root 1 plus x squared. And so what we get finally is we get the square root of 1 plus x squared, that's secant theta, but then all of that is squared, and so those just cancel out, and I just get 1 plus x squared. Isn't that beautiful? And then we have proved the inverse tangent is a derivative of that is 1 plus 1 over x, 1 plus x squared. You can do that for all 6 trig functions and find the inverse, the derivative of their inverses. We did 2 of the proofs. If you want to do some of the other proofs for fun or look them up on YouTube, you certainly can, but I'm just going to leave that for now. Now we're just going to use these derivative formulas to do a few example problems. So number 5, find the derivative of f of x is tan inverse of x squared. So we can just apply this rule right here. We don't have to reprove it every time. You saw me, laboring through those proofs. It's quite a bit of work. We're just going to use it. So f prime of x, let's just use the formula for tan inverse. It's 1 over 1 plus x squared. But this serves as our x, right? So it's 1 plus 1 over x squared. We have to use the chain rule. The chain rule says take the derivative of the outside function, and the outside function is tan inverse, but leave the inside piece alone. Leave the x squared alone. That's still there. And then multiply by the derivative of what's inside. Derivative of x squared is 2x. This would be best written as 2x over 1 plus x to the 4th. All right, that would be our derivative there. Think about that one. Let's try one again here. Here you may notice we have the product rule, x squared times sine inverse x. All right, so when we do our product rule, remember it's derivative of the first, so derivative of x squared, 2x, times the second, sine inverse x, plus the first, x squared, times the derivative of the second, the derivative of sine inverse of x. Of course, you don't have it memorized yet, so you're going to be going back and forth to this list up here. In this case, you can see it right here. This is the one we proved earlier, 1 over square root 1 minus x squared. So we got that thrown in right there. You could maybe rewrite that or simplify it more, but I think that's totally valid right there. All right, pause the video and try 7 and 8. Come back to see how you did. Okay, again, we have the chain rule here on number 7. The inside function is 3x minus 1. The outside function is cosine inverse. If we use, and this is one I did not prove, if we use the rule from above, the derivative for the cosine function, cosine inverse function is 1 over the square root, that's negative 1. And that's because, when you take the derivative of cosine is negative, if you happen to do the proof. So negative 1 over the square root of 1 minus x squared, but leave the inside function alone, right? So don't just write x squared, write that 3x minus 1 there, times the derivative of inside part is 3. If you clean that up a little bit, it would look something like this. Negative 3, because 3 times negative 1, over, and I'm not going to distribute that bottom piece. I'm just leaving it 3x minus 1 quantity squared. You could multiply that all out, but I'm just going to leave it for now. 8, find the equation of the line tangent to the graph of Ix equals sine inverse x. So this one, there's no chain rule. It's just the straight up inverse sine function. So the derivative, we'll just use the rule that we've already proved from above, would be 1 over 1 minus x squared. But we want to find the equation of the tangent line at x is 0. So let's go ahead and plug in our 0 into our derivative. We get 1 over the square root of 1 minus 0 squared, and that will just be 1. So our value of our derivative is 1. That's our slope, right? But remember, when we write an equation of a tangent line, we need a slope and a point. So let's get the point by just plugging in 0. Sometimes I do it in the other order, but now I'm doing it in this order. We want sine inverse of 0. Now, that value is just 0. Remember, when we're doing sine inverse, we only consider the domain to be, between the negative 1 and 1, and our range, our output values, we're only going to accept values between negative pi over 2 and pi over 2. So even though, of course, on the unit circle, you can go infinitely many times to find a spot, we're only going to use that one spot where x is 0. So we have the value there. Our point would be, when you plug in 0, you get out 0. When you plug into the equation of the line, you get y minus y1 is equal to m times x minus x1. You simply get the line y equals x. At this point of the video, you might notice that there's a problem below, a word problem, but it's not on your notes, and that's because we won't be doing it. This video is already 33 minutes. I figured that's long enough. We're going to try and save some application problems for class. That'll be the end of this video. See you in class.